big issue. So if you look at this, from 2012, the amount of light pollution here is increasing incredibly. So actually, based on this information, and you search for a candidate to host a new telescope is a must. Next. Oh, we started our search by using the DEM with a very high resolution. Okay, so I want to highlight that this work is a part of a big collaboration and stuff in Egypt and in different university, and also people from Trieste in Italy. So this work is a part of a paper. I'll show it after by the end of this presentation. Okay, so you can see that this is the digital elevation models. Next, for Egypt. So after this, we put some conditions to select the sites. Okay, so for the first, it should be high. Okay, to avoid the turbulence of the turbulence of the atmosphere. Let's say more than 1,000 meter. Also, the second parameter is the accessibility. The third parameter is to be away from the cities to avoid the light pollution, scattering. Okay, and based on this, we got around 8 sites. Again, next. Okay, so we compared our site with one of the very interesting publications by Aksakar in 2020. Okay, so we find that most of our candidate sites have a good let's say value in Aksakar, except this one. The next. And we eliminated this one. So we focused on 7 sites in Egypt. Okay, so the 7 sites. First of all, we looked at the Zenith, that's sky practice, from the online internet data by VERS. We find that those are excellent in terms of the light pollution, and this is a very important point for the optical observation. Next. Again, the air temperature for all the sites are good. Yeah, they're varying, but it generally are good. Okay, next. Also, we discussed or explored the direction of the wind direction and its velocity, and we find that it's all in all direction, which is good. In all the year, so it will decrease the turbulence around the region. So this will make your telescope all the year stable. So next parameter is next. The next parameter is the number of clear nights for each site, and for this we consider this reference to that the cloud coverage less than 25% per year. So this is our result. We found that an excellent values for the site one. We have more than 280 nights, and for 6 and 7 we have more than, or we have almost 290 clear year per the year, clear nights per the year. Okay, so all of this also are taken from the ERA 5 data. Next. An important actually parameter is the AOD. The AOD is the measurement of the total aerosol distributed through a column of air extending from the Earth's surface to the top of the atmosphere. And here that a full image of Egypt for the AOD. So those are also our candidate sites are located here. So you can see that this area, which is Sinai, is very good in terms of the AOD. Next. Okay, so seismological parameters, and it's important, and sadly I can say that this parameter is very important due to the effect of it. So you can see that the collapse of one of the let's say historic or radio astronomical telescope in the world, which is the Arecibo, which is collapsed due to an effect of the seismic activity. So you have to consider this parameter in our study and to search for a new telescope. So I think most of us want to pay around $1 million, and then let's say earthquake come to destroy all what they do. So we have to consider these parameters. Next. Okay, so to understand the seismicity of the region in Egypt, we put let's say a map for Egypt, okay, and try to gather all the online data from different catalog, and this is the source of this catalog, to find that if the strength of the magnitude that happened during these areas on Egypt, and this is these are the strengths. Of course the red one is the higher one, and so on. Again, sorry, next. Okay, so we focused now on our 7 sites. So for the 7 sites, we found that we have one site here is a very good and have a low seismic hazard, and 2 in Sinai have a high seismic hazard. In the region of the the Hurghada or the Red Sea, we have also one low seismic hazard, and the other 2 intermediate or moderate, and 1 high seismic hazard. So this should be taken in consideration. Okay, next. To understand all the process, we combined all of these parameters, and let's say we did an overscore for all of these parameters. This ends that these parameters from 1 scores from 1, 0.9, 0.82, 0.85, and 0.0857. Those are the scoring for those parameter. We actually from the 7 we find that 4 are good for accessibility and so on. So we concentrated on this 4 sites. Next. Okay, so just to remember you that all of this work and more are done in this paper. So I invite you to take a look for this paper for more details. Next. So I have to acknowledge the people working on this day, on this paper, and actually both I mean some of them are attending here in this meeting. I would also acknowledge the general support of the AFAS and the organizing committee to support me to I present my work, and actually without their support I wouldn't be able to attend. Finally, thank you for your attention. I hope in time. Thank you. Yes. Sadly, you have thought. Okay.
Excuse me, how does seismological hazard change dramatically within 10 kilometers?
Okay.
Second question, please. Do you have map for water table, turbulence?
Okay, so this work is actually focused on some parameters like the air temperature, humidity, and so on. But actually, it could be extended to let's say include air turbulence and
good day to all of you.
other parameters. But I think for this only we just mentioned those parameters. Actually, it takes too much time and too much paper to yeah, introduce this. For the seismic hazards, we actually I'm not specialist
I mean,
in
how
point.
change this lot of change in hazard within 10 kilo?
Okay, so it's not related only to the point that the earthquake happened and the
Good day to all of you. I am Yosef Hatch and I am very much pleasure to present my research proposal in front. I will introduce my
I
research.
just said I'm not expert in the seismic
Okay.
points. You can
I will introduce
the
my
authors of these papers and can contact all, and you can contact with my college from Trieste or even from NRIAG.
Okay, thank you very much.
You're welcome.
Any further questions? One more question? Okay, well, let's thank our speaker again.
Thank you.
Okay, we have as our last speaker here, Dr. Yosef Hash, and he's going to be talking about characterizing and comparing astroclimatic parameters in the free atmosphere of the MENA region through NCEP and NCAR reanalysis, a comparative study. So is he here or he's online? Is that an online talk, sir? Say it again, please. You're supposed to be in person? Okay. Well then, if he's gonna come and we have time for him, that'll be great. But we were thinking, Dr. Yosri and I, were thinking, or Yosri was thinking, we should do a panel of the three people who have spoke, and they could answer more of your questions. We have somebody, for instance, online who already has a question for the first speaker. So. Oh, he has a video. Oh. Oh, I apologize. Okay. We'll still try to have maybe 10 minutes of question and answer session. So, but go ahead, right ahead. He should have about 15 minutes, I guess, for his talk. Hard to get that done, huh?
Good day to all of you. I am Yosef Hatch and I am very much pleasure to present my research proposal in front of you. Today my research topic is titled, Characterizing and Comparing Astroclimatic Parameter in the Free Atmosphere of MENA Region through NCEP, NCAR Reanalysis, a Comparative Study. I will introduce my research subject by qualifying sites for the installation of an astronomical observatory. This operation crucial is carried. Good day to all of you. I am Yosef Hatch and I am very much pleasure to present my research proposal in front of you. Today my research topic is titled, Characterizing and Comparing Astroclimatic Parameter in the Free Atmosphere of MENA Region through NCEP, NCAR Reanalysis, a Comparative Study. I will introduce my research subject by qualifying sites for the installation of an astronomical observatory. This operation crucial is carried out in several steps which can be summarized in 2 steps, pre-selection and installation of the instruments on the best pre-selected sites. However, there are several problems that hinder this qualification. I will cite in particular. Impossibility of carrying out measurement campaigns generally linked to the problem of accessibility. Absence and discontinuities of measurements. In our study, we tried to find other alternatives of astronomical site testing for wave time and the cost of observations. The solution proposed in our study for the MENA region, Middle East and North Africa, is based on the one hand, choice of NCEP, NCAR reanalysis system database as an alternative to direct measurement at the observation site. And on the other hand, the use in our study of new approaches which currently apply to the characterization of astronomical sites and which generally relate to several site selection factors instead of using the classic scheme. In this works, we have carried out 2 studies of sites characterization in the MENA region by using astroclimatic parameters obtained from reanalyzed data covering 2 periods. Based on several works, notably that carried out by Gesum et al. In 2014, we already undertook a site preselection study on a main list comprising 18 sites in the MENA region. This allowed us, after a scientific classification, to reduce the main list to 6. For the first period, we are today undertaking the comparative study of the 6 pre-selected sites in terms of dynamic turbulence based on meteorological data. The second study spans a single year and covers the same 6 sites from the main list to examine aspects related to optical turbulence. This work constitutes participation in the pre-selection study of future astronomy observation sites in the MENA region. The main objective of this study is to identify the best location in the MENA region which can be recommended for astronomical observatory installations in several countries of MENA. Then, improving the characterization of sites for the astronomical observation. Finally, is to show the usefulness of reanalysis data for the characterization of sites. In this study, we used NCEP, NCAR reanalysis data which provide global coverage with adequate temporal resolution. The parameters analyzed include wind speed and its direction, height, and pressure. We also analyzed integral parameters such as seeing, coherence time and isoplanatic angle. We proceeded by processing reanalysis data in free atmosphere. We analyzed the different astroclimatic parameters of the sites in the MENA region in order to be able to classify them in terms of atmospheric turbulence. The astroclimatic characteristics of each site were compared using statistical methods, monthly, seasonal and annual, to identify significant differences and understand the particularities of each site in terms of atmospheric turbulence. Cumulative probability distributions and seasonal trends of wind speed at the 200 millibar level were plotted for each site. The vertical profiles of the refractive index structure constant and probability distributions of integral parameters were also generated to visualize local variations. The results were interpreted to identify the most favorable sites for astronomical observations. We present here a brief review of the different parameters of atmospheric turbulence introduced in this scientific research work. We cite in particular the Richardson number, the average speed of turbulence, as well as integral parameters such as seeing, coherence time and isoplanatic angle. In addition, we present the equation translating the Todorski model which allowed to obtain atmospheric turbulence data from meteorological data. The topographic map, obtained by processing satellite data, shows the different sites studied and their elevations, Aklim, Klina, Diriba, Mishbi, Saitu and Shams. The colors represent different altitudes, with color bar on the right indicating elevation in meters. Blue areas represent negative altitudes and brown and white areas higher altitudes. The highest areas are mainly found in the mountain ranges, particularly those of the High Atlas in Morocco. To explore the seasonal behavior of wind speed at the jet stream level, we plot the monthly average value of wind speed during the period from 2011 to 2015 for the 6 locations in the MENA region. The 2 sites Mishbi and Shams present the same seasonal behavior characterized by low values of wind speed in summer and high values in winter. The amplitude of the speed variation is the highest. However, the Aklim site presents an inverse seasonal behavior with a low amplitude. It is the same for the Klina site. These differences may result from variations in geographical locations and atmospheric conditions. Indeed, the 2 sites Shams and Mishbi benefit from being close to the Red Sea on the side of Mishbi and the Arabian Sea on the side of Shams. Hence the probable existence of a cold current flow in advance of the seas that helps create a temperature inversion. We present here in the figure the statistical results of the wind direction at the 200 millibar level. The color distributions in this figure represent the scope of wind speed values. For the sites of Aklim and China in North Africa, we see that the wind speed has a single predominant direction, the east component for Aklim and the west component for Klina. The main distribution range of wind speed values is less than 30 meter per second for Aklim and then 60 meter per second for Klina, which is consistent with the statistical results of wind speed indicated by the histograms figure. For the three sites Mishbi, Shams and Sai-2 in the Middle East, the wind speed presents two predominant directions, one is towards the west in the case of high speeds and the other towards the east otherwise. Indeed, the winds come in these directions due to the atmospheric flow on a large spatial scale. Now we move on to the parameters related to the aspects linked to optical turbulence, and we will start with the Richardson number. In the figure below, we present the profiles of the inverse Richardson number for each site studied. For the low-latitude sites, Diriba, Shams and Sai-2, there are visible peaks for the profiles of Richardson number inverse in the troposphere region, around 14 kilometers, and whose intensity decreases with altitude. The more the value of Richardson number inverse increases, the more the atmospheric conditions are unstable and easily produce dynamic turbulence. For mid-latitude sites, Aklim and Klina, the tropospheric region is between 9 kilometers and 10 kilometers. The intensity of the peaks in this region is very strong for the Klina site. However, we note the presence of another peak of moderate intensity at 25 kilometers altitude for Aklim. In general, we can say that the atmospheric conditions at the Aklim site are more stable than those at other sites. Therefore, a low probability of turbulence triggers in Aklim compared to other locations. The refractive index structure constant is of great importance in determining the force of turbulence at any site. The adjacent figure shows the probability distribution of vertical profiles of refractive index structure constant for different quartile values. For the two mid-latitude sites, Aklim and Klina, the refractive index structure constant value increases in the first 11 kilometers with altitude and reaches its maximum at the height of jet streams. The same for the Mishbi and Sham sites, but with a fairly low jet stream height. Between the height of jet streams and 24 kilometers, the value of refractive index structure constant decreases with altitude until reaching low values. For the other low-latitude sites, the vertical profile of refractive index structure constant presents a different behavior, which is manifested by the presence of two peaks. The first at around altitude 9 kilometers and the second around 14 kilometers. The variations of refractive index structure constant at the Diriba sites and Sai-2 are almost identical. Likewise for Shams and Mishbi. This is probably due to a similarity in the topographical characteristics of the site. The seeing is one of the main parameters of high angular resolution. The figure shows the statistical results obtained for this parameter from the reanalysis data for the year 2011 on the 6 sites in the MENA region. The mean, median, and quartile values of each site are also represented in this figure. We note that the Diriba site presents 95% of seeing values lower than 0.58 arcsec with an average of 0.5 arcsec. However, there is a very small lack of seeing value. The same thing for other low-latitude sites which do not have many small values. Thus, we can say that the Aklim site benefits from periods of the year where the state of atmospheric turbulence is minimal, which is favorable for an imaging observation which is exigent in turbulence conditions. 25% of seeing values at the Klina site are greater than the value 0.63 arcsec. Klina has lower sky quality than other sites in terms of atmospheric turbulence. The second parameter of high angular resolution is the coherence time. The temporal evolution results of this parameter obtained from reanalysis data are shown in the top figure. On the bottom figure, we represent temporal coherence distributions, blue histogram, and cumulative distribution functions, red line, from reanalysis data. The mean and median coherence time values obtained from the data for the 6 MENA sites are also shown in the figure above. We have also presented the different quartiles in the bottom figure. About 75% of the coherence time values are above 6.56 milliseconds, 4.95 milliseconds, and 4.60 milliseconds respectively for Diriba, Psi2, Acclim. Atmospheric turbulence evolves slowly in the Diriba, Psi2 and Acclim sites, which has the largest value of the coherence time among the others, which will therefore allow adaptive optics systems to effectively correct distortions due to atmospheric turbulence. We also note the existence of a continuous period of the year where the value of the coherence time is high for the two sites Mishpi and Shams, which is beneficial in the case of using adaptive optics instrumentation. The last parameter of high angular resolution is the isoplanatic angle. The mean and median isoplanatic angle values obtained from the reanalysis data for the 6 MENA sites are shown in the figure above. On the bottom figure, we represent the temporal isoplanatic angle distributions, blue histogram, and the cumulative distribution functions, red line. We also presented the different quartiles. About 75% of the isoplanatic angle values are above 1.64 arcsec, 1.61 arcsec, 1.60 arcsec respectively for Psi2, Diriba, Shams. The effect of atmospheric turbulence in the Middle East site is weak over a large area of the sky. Likewise for the two low-latitude sites in North Africa, Diriba and Mishpi. These sites are qualified as the best in the MENA region. The highest value is recorded for Psi2 with a value of 1.64 arcsec for more than 75% total values. That said, the field of vision at Psi2 is very large and the correction carried out by adaptive optics systems would therefore be very efficient. In conclusion, we can say that in terms of dynamic turbulence, 1. The analysis of the seasonal behavior of wind speed at the jet stream level allows on the one hand to quantify the value of the speed and on the other hand to know the periods of the year when there is a low value or a high value of the speed. 2. The Richardson number is unable to quantify the strength of turbulence. It can be considered as a tool to check the consistency of measurements of turbulence that will be carried out in sites not yet prospected. The figure below shows the classification of the different sites in the MENA region in terms of optical turbulence. According to the statistical results, we can say that the best locations in the MENA region which can be recommended for astronomical observatory facilities are Diriba, Acclim and Psi2. In addition, the results presented here constitutes a potential reference that will enable astronomers to test and develop ground-based optical astronomical telescopes and AO instrumentation at the 3 sites in the MENA region. Finally, these results presented here are supplements for further investigation of the site characterization in terms of optical turbulence parameters. This is the end of my presentation and thank you very much.
Questions, but we do have time if the 3 speakers, if Dr. Graham and Dr. Marcos and Dr. Darwish would like to come to the podium for just a few minutes, 5 minutes or 10 minutes, and answer any questions that people have. Because I know, for instance, for Dr. Graham, there was one question from Evan Irwan Akbar, who asked, are the other 2 speakers here? Come on up, yeah. I think we need, is Dr. Marcos here still? Okay. Well, anyways, good. So the first speaker, you have a question. Evan says, you mentioned that the resolution of the reanalysis data is not adequate for turbulence in terms of millimeters and millisecond resolution. So what is the best method to validate it? Using radiosonde data and launching balloon, measuring seeing using DIMM and other methods, perhaps?
Yeah, observations, direct observations.
Direct observation.
That's really the only way to validate. There are proxies. As I showed there, in fact, the last talk was talking about Richardson number, although it wasn't think the conclusion weren't so favorable. The Richardson number, if you've got a very high resolution model, in the case of the WRF model, which is a regional climate model that you can run down to as low as 500 meters even, and you can have, I typically run it with about 70 different levels in the atmosphere, but you could run it with hundreds. And in that sort of case, you're not directly resolving features in the atmosphere, but you're resolving more of them. And you'll get a result that's at least a reasonable proxy for what you would achieve in measurements. But it's not a solution, but it's a good proxy, and it'll point in the right direction. But at this stage, the only solution is still observations.
Yes, sir.
Nothing about it, but LiDAR, I know, is used for atmospheric studies. Is that something that can tell you rapidly what's in?
I know they use them at airports, David, and yeah, and also wind profilers. I'm not aware of any studies offhand, to be honest, David, that have tried to do that. There may be some value in attempting to do it, but a wind profiler costs about 100 grand. So they're not exactly two a penny. It would be worth actually just at some stage linking up actually with aviation meteorologists, because they know an awful lot about turbulence as well, and turbulence is becoming a lot more of an issue in aviation, you know, due to climate change. So that's another area of potential exploration and opportunity.
I suspect also space ranging, people who are using lasers to find satellites, whatever. They do adaptive optics on those systems. So
okay.
It's true.
Yeah. But that could be sort of information that's not readily available.
Yeah, I don't think there are any there's a shortage of potential and possible collaborations we could make to improve our knowledge in this area. Certainly. To be honest, I don't know enough about them to be able to comment any further, David. Sorry.
Well, we have probably time for another question. Go ahead. So that people can hear you online, do we have a mic at all? Thank you very much.
I want to ask about the lessons you learned from looking at good sites in Kenya, and if we are able to get these lessons in our search for good sites in Egypt also.
I'm sorry, I didn't quite understand that. Do you mean extrapolate what we're learning in Kenya to Egypt?
I mean for looking for good sites for the building new telescopes in Kenya. You mentioned your lecture now,
Yeah.
talk. We are now looking for good sites also in Egypt.
Yes.
And if we are able to get your lessons you learned, because we have, for example, an accessibility problem in one of our sites that we can not reach in order to put the site testing instruments. And we started working with only one site. Is it possible to start working with one site and then until we have solved the accessibility problem of the other sites, or no?
I think in the case of Egypt, as Mohammed explained in his talk, I think there are definitely some good sites there. I wasn't aware actually of all the earthquakes that happened near Sinai. So I guess that mitigates the excellent cloud-free conditions. But in Kenya, we've narrowed it down more or less to three or four, and I think it would probably be wise. And we've got three sets of weather stations, which of course we could move to different sites if some of the currently indicated sites don't prove to be as good as we envisaged. Because remember, the reanalysis, as good as it is, it's the most accurate model we have. It's still not truth. And the only way you can validate it is with observations. And it may be that actually the observations at one or two of the sites aren't as good as we expect, but in which case we can move them somewhere else. So yes, I wouldn't put all your eggs in one basket, or eggs in one basket, as the saying goes, to at least survey the top two or three, I think would be wise.
But I mean the other site, we have two sites now. One site is very good, and we have road to that site,
Yeah.
and we can access it easily. The other site is very difficult to access.
Okay.
The terrain of the mountain is very difficult, and we cannot send the site testing instruments like DEM and other station and
Yeah.
so
Yeah, I think in that case you need to use some sort of decision model, as the second speaker was mentioning, this sort of mathematical decision aiding mechanism of some sort. And there are plenty available in sort of desktop GIS which will help you do that. You just need to allocate a weighting to the that reflects the importance of each parameter to you. And different organizations will allocate different weightings. I mean, if it's all about money and time and getting something built as quick as possible, you'll allocate different weightings to something where it's more about training and education. So,
If we have one side, then how we compare? Compare with what?
if you have
If,
one side,
if have one side only, then how we compare with what?
if you have only one site,
Yeah,
well,
in the same point,
well, then obviously you don't have a choice and you've got to go with your one site. But I would still recommend undertaking both
I mean,
modeling
need
and
comparison.
observational studies.
I mean, we need comparison with.
I mean, you can compare with other sites in other countries, certainly that might be at a similar latitude or have similar environmental conditions. But I would strongly recommend that all sites characterization or site selection studies have some sort of modeling and observational aspect to them both, where the modeling can be validated with real observations.
Okay.
Well, we've come upon 3 o'clock, guys, and I don't
Second
want to
question,
stand
please
you
answer.
between you and your
Second-
coffee.
Okay,
But,
okay.
oh, sorry.
Small question.
Well, if people don't mind,
Excuse me, I have used Mira 2 model. Is there any comparison with Mira 2 model with another model?
I'm not sure.
would you like him to come up and talk to you about this?
We actually used the
Mira 2 model.
Mira 2 models.
Oh,
okay?
Mira,
Yeah,
yes,
yeah, data.
yes, yeah.
So Professor Nasser asking if we have another data
Another
to compare
comparison
with.
with another model.
Do we have a more higher resolution data to compare with if it's
The current highest resolution reanalysis is about 15 kilometers or so, but there's a new project called ERA6 that'll be coming out, I think
Era
next.
6?
Yeah, ERA6.
Era 6.
ERA6 will be coming out, and that'll be even higher resolution. Yeah, and I think that's going to be out within the next year.
Okay.
You can run your own model. That is, you can run a very high resolution model, as I was mentioned just in response to the first question, such as WRF, which is the example I showed briefly in my talk. You can run that up to, well, hundreds of, 500 meters, maybe a kilometer resolution. It won't work at any higher resolutions because then you have to start resolving features explicitly, because models don't solve the physics of the atmosphere directly on at the actual scales that, for example, a small little cumulus cloud, a model cannot resolve that explicitly. It uses parameterizations, a statistical technique, to bypass things it can't resolve. So a model can't really be run less than, depends on the type of weather pattern, but less than maybe a kilometer or 500 meters, because now we're getting down to scales such, I mean, where the we're getting close to, the turbulent cascade at Kolmogorov's inner and outer scales. And in those cases, you need to actually resolve the features explicitly. But that's a whole new ballgame. It's a whole new type of model to do that.
Okay. Thank you.
I think we should say thank you to all our speakers. They may hang around for a couple more minutes if any of you have any questions for them. What I'd like to say to yours, I think it's like,
I know I didn't. Yeah, yeah.
so that's something that's very significant.
Yeah, and it's getting back. I know. Yeah.
And for you, I think it's not just the fact you got like this, but what is the growth perceived around with it?
Yeah. Hi, Yoshi. How are you? How are you? Good to meet you. Good to meet you. Yes, yes.
I was asking,
Yes.
because we have two sites, Muhammad
Yes.
and his
Okay.
research,
Yes. And the one on Sinai.
one in Sinai and one in Red Sea.
Okay. Yes.
The Red Sea site is very difficult to access.
Okay.
The terrain of the mountain
Yes.
is very difficult.
What height is it?
It is about 1,300.
Okay. Yes.
The other one in Sinai is 1,650.
Yes.
So this one in Sinai, we already bought
Yes.
the site testing instruments.
Yeah.
Because, it is
Yeah.
accessible.
Yeah.
The other one is not. It's very difficult to access.
Okay.
So how can we start with one site only and compare the results with theoretical?
Yes, yes, you could. You could. If you install instrumentation on the first site and then correlate it, do some multi-regression analysis with the reanalysis, and then go to the second site, get the reanalysis, and then try and go backwards and work out what the observations might be at that site. So reverse the auto regression. So if you,
Nasser is objecting about this feature.
No, I don't like. I don't like.
yeah.
we should compare at the same
Yeah, yeah.
Start now. Hi, everybody. I am Zuhair Ben Khaldoun. I supposed to give a first talk this morning, but my flight was delayed. I am sorry for that. I will share this session and where we have 4 talk, about 20 minutes each. We will speak. We will have Warren Skidmore. We're speaking about establishing the scientific and technical aspect of a future astronomical observatory. He's an invited speaker. We will have Constance Walker. She will speak about the protection optical observatory site from the growing satellite constellation interference. And after Ramoto will speak about the dark sky protection in South Africa, potential model for other observatory in Africa. And finally, we will conclude with Federico Di Verno from SKA Observatory to opportunity for Africa and challenge with new large satellite constellation. So Warren is online. You can share your screen, Warren, and the floor is yours. You will have 25 minutes for your talk. Thank you.
Thank you, Zuhair. I'm sharing my screen now. Can you see it?
Warren, we don't hear you.
Yeah. Hello, Zuhair. I'm speaking and I'm sharing my screen. Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, it's okay now. We're hearing you. The floor is yours, Warren.
And you see my screen? Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, it's okay now.
We can hear you.
We're hearing you. The floor is yours, Warren.
And you see my screen? Hello. I'm sharing my screen. I'm speaking. Hello, Zuhair. I'm speaking and I'm sharing my screen.
Yes, it's okay. Yes, go ahead. We are hearing you and we see your screen. You can go in.
Okay, there's a very strong echo, and we were getting several repeated echoes. I wasn't repeating myself, I promise, Zuhair. Thank you very much for your patience. So yeah, my name's Warren Skidmore, and I'm ever so sad that I can't be with you guys in person. It just wasn't possible for me to travel. We've had some great talks about establishing projects and why we want to establish projects and where we want to establish them and things like that. And there's a component of establishing a new observatory project that is quite important and has become more important in recent years with new project management techniques that are and new system engineering processes and things like that. And that's making sure that we, from the very outset of the project, we do our best to understand the scientific goals of the project. Exactly what Abd was mentioning in his talk. We need to understand the science, and it's not everything we have to do. There's a lot of things we have to do to establish a project, but understanding the science is very important. There's been a lot of discussion about what's going on in Africa, in the continent of Africa. There's lots of projects that are going on. I'm going to focus on observatory projects, a telescope plus instruments, big projects. But there are lots of instrumentation projects which are going on, smaller scope, and a lot of the sort of things I'm going to talk about are kind of scalable. But my focus is the establishment of an observatory, and I won't repeat this. There's lots of good reasons why a project to build an observatory may arise and be carried out. Mariana spoke very well about those, you know, the international collaborations and cooperations, all sorts of things that come about through building observatories. But one of the things we need to know from the beginning is understanding the kind of science we want to do with the observatory. And there's many reasons for this. You know, number one, it's key for promoting the project. Having some sort of high level, you know, grab some science stories that grab people's imagination and excite people. That's very important for promoting any project. And so some sort of high level description of the science goals in some sort of science case, science book is important to have. When you're communicating with other astronomers, you know, the future users of the observatory, they want to know what the observatory can do for them. So if they see science cases that are close to their own areas of science, that's a good thing. And also the development of a science book or a detailed science case, collecting everyone's ideas. That's a very good opportunity to engage with the astronomy community, whether that community is, you know, the astronomers within a country or within a region or internationally. It depends on the project, but building up a science book is a good chance to build a connection with future users of the observatory. And the technical information that you gather when you build a science book, when you capture everyone's ideas, that technical information, what type of observations do they need to do in order to do the science, that's what guides the design of the project. Of course, one doesn't come without the other. You know, if you had no constraints, everyone would want a 150-meter telescope that had every instrument possible on it, built on a 17,000 foot high mountain, and that's not possible. So it's a sort of an iterative process. Have some idea, develop some science ideas, develop some kind of design, and the things go hand in hand. Yeah, one feeds back to the other once you start this process. Now, understanding the science goals is also important for understanding where you can build the observatory. What do you want the observatory to do? If it's a seeing limited optical observatory, you want somewhere that's got lots of clear nights and you know, dark skies. If it's lots of adaptive optics science, you want a place which has very high, very good atmospheric turbulence properties, and you may be less worried about the total number of clear nights. It's different parameters would have different weights depending on what sort of science you want to do. And across Africa, there's a lot of different sites. Each one of them has its own qualities. So you know, you need to know the science you want to do so that you can you know, identify the parameters, the qualities of the sites that you could consider. So when a project is born, when people start to have the ideas, you know, a whole bunch of things need to start to happen. You know, think of some cool science, think of a design. You know, I'm here because I got to know Yosri and the folks that are involved in the ELOT project, the Egyptian Large Optical Telescope project. They have an idea for a design. You know, you can think about the kind of science you would do with that. And and once you have a design as well, you can start to think about, you know, how much it's going to cost, the schedule, where you're going to get the money from, start to define this project scope, develop a partnership. You know, if you have a very ambitious project, you may need to spend time building up the partnership so that you have the resources available. And then, you know, there's this thing at the bottom, begin the project integration management. That's how you start a project formally. You know, it's all written down in textbooks. I don't know if you can see my little picture. There's lots of project management textbooks. It's all standard sort of stuff for starting off a project. Now, this list of things, I say, is not a chronological list. They all have to sort of take place. They may not all start at the same time, but they will definitely overlap in time, and they'll often need to be done before you have any significant resources available. So how do you develop a science book and get technical requirements and things when you don't have money to spend on the project? You know, I'm not sure how you know, I don't have an answer for that, but these are the sort of things you have to navigate through as you start a project off. But you know, the number one thing, or the main thing, is really understanding the science that you want to do with this observatory. Now, lots of the partners will have additional goals, and these are things which are not astronomical. You know, it's workforce development and things like that. So those are also factors you have to consider in the larger project. But what I'm focusing on here really is what you do about the science and how you understand, how you gather the information to understand the science you want to do. So in textbooks, you often see sort of pictures like this, very idealized. You know, someone's got an idea, you know, let's build an observatory, you know, so you get some science cases, come up with a design, iterate it a bit, and you know, the project will go. But this is not reality. All kinds of things happen to disrupt this idealized picture. And something which is probably a bit more realistic is that you have each line here, each colored line represents in when I was making this picture, a partner. Might be an institution, it might be a country, but different partners with different priorities. And you know, and someone at the start thinks, let's build an observatory, and they start to accrete, you know, build up the partnership and find out what the partners want to do, and eventually, you know, some resources are committed, and eventually people, or the partners align, and you get a nice coherent picture of the observatory. And this is kind of a little bit like this idealized picture rolling along in time, and eventually everyone hopefully will converge, and you can really formally push the project forward. And this process can be quite difficult, because everyone has different ideas, different things they want to do, and to get everyone to converge can be very difficult process. So you know, back to this point, having a good idea of the science goals is important. So you need to develop something like a science. I use two terms here: science case or a science book. You know, I work for the 30-meter telescope project, and we have the TMT detailed science case. But I don't like that name, because the detailed science case consists of lots of science cases. So, you know, I prefer the term a science book, a big, thick book that has all the science cases in it. And a lot of projects use that terminology. And you have to have, when you start to develop this science book, some idea of the observatory. You know, what sort of scope it'll have. For the E-lot, 6.5 meter mirror with some sort of imager and perhaps a spectrograph. I'm not sure of all of the ideas, but there'll be some general constraints which will help to guide the science ideas, and that will also help you with developing the idea for how much the whole thing's going to cost. Basically, what resources you're going to need to build the observatory. So when you're building the science book, you can have some broad science areas, high-level science areas, and you don't need to have every single possible science case in your science book. You just need to have some representative cases which define observing capabilities, which will service other areas of science. So you can get going relatively modestly to begin with, and from these science cases, you develop the top level science requirements, and you can use this when you're talking to other astronomers, saying, we're going to have this type of instrument, this spectral resolution, this wavelength coverage. These are the sort of top level requirements that you can discuss with the community. So you have to start to have communications, with resources, talking to other partners or potential partners, or people at the university if you're a large institution, and then you also need to communicate with astronomers, and that can take all kinds of different forms, but you have to communicate with them to gather their ideas, get a representative set of science ideas, and like it's an iterative process. Once you've got some science ideas, and you know what sort of capabilities you need or you want, how does that actually feed back into the process? So you are in a sort of a chicken and egg situation. Which comes first? The chicken or the egg, the science requirements or the or the science goals? And there isn't, all you need to do is pick one, start the process, and go back and forth a couple of times. So communicating with the community and with all stakeholders is key, and you can start the process off with some fairly modest communications, a workshop, email newsletters, and open calls to the community for input, that sort of thing. And all projects kind of go through this process. They all develop science cases or science books. You can see in the top row here all the different kinds of science books. Most of them are called a science book. And this second row is the requirements, the technical requirements that come out of the science book. And I wanted to note down here, for SKA, for example, the science book is thousands of pages, very technical, almost like lots of observing proposals stapled together. For TMT, it's for my project, it's a very sort of narrative kind of document, a couple of 100 pages long. And then for the new robotic telescopes, it's pretty short, just a few pages long, really, with just some exemplar observing programs to make sure that they define the full scope of observing capabilities that they need. Now, when you're collecting people's science ideas, over on the right-hand side here. Every astronomer has some idea of some cool science they want to do. When you collect that information from them, you must collect the technical information at the same time. It sounds obvious, but you've got to set up a process that does it. And how you set the process up, I'll talk about that a bit more in a moment. But I wanted to give you a bit of a historical perspective. You know, my project, 30-meter telescope, has been around for a long time. These green boxes in the middle show the 4 iterations we've had of the TMT detailed science case, our science book. But looking here towards the earlier part of the project, you know, there were a few ideas, 3 different projects for a 30-meter class telescope that merged to form the 30-meter telescope project. And those, each project had some sort of science book, and we had a science advisory committee that pulled all that together, and you know, it was representative of many areas of astronomy, and they really wrote the detailed science case. They had additional input from all of these early instrument studies as well. Each instrument that was proposed for the 30-meter telescope came with a science case. So they had a lot of information that they could pull together, and the science advisory committee, a group of about 15 people, wrote the first detailed science case. And then a few years later, we revised that, and we wanted to make sure we reached out to as many people as possible. And we set up these international science development teams, very similar to the Rubin Observatory science collaborations. You know, topical groups, you know, one on black holes, one on exoplanets, one on star formation, galaxy formation, topical teams. And they wrote our 2015 version of the detailed science case, and there were hundreds of people involved in that that gave input. So you need to go through this process of developing a science book, and you have to sort of set some ground rules. Who will be the people that really approve this the science book? I've got this word here in the top row. They approve it. They may not write it necessarily, but they accept it as a good, valid document. And it might be, at least for the case of TMT, it's the Science Advisory Committee that formally approves the detailed science case. But they get advice from other, the system engineering group and instrument teams, and also the Science Advisory Committee themselves are very much involved in in keeping the document up to date. So when they approve it, they know what they're doing, and you need to have some sort of group that will approve the science book that you develop, but you need to identify one person to lead all that work, make sure it's all coordinated, and each project will have various engineers that start to get involved, or people that have developed projects before, and they can give you help and advice and actually do work on developing project documentation, early project documentation, developing the requirements from the science cases. This is the thing which I find most interesting is what process do you use to collect the science cases and the technical information from the community? How do you do that? So you have to think about who will be providing this information. Is it a group of individuals like the TMT SAC back in 2007, or is it lots of people like big projects tend to do these days? And how do you kickstart that process? Most projects have annual science workshops or something like that, some way of getting people together to discuss science and to contribute to collecting this information together, and then decide on what the science case is supposed to be. Do you want it to be a nice book that you can read, or do you want it to be a very sort of technical document? That depends. Different projects use different versions, different type, different formats. For TMT, it's more of these manuscript. It's a bit like a science paper, but a big one. And everyone writes their parts and puts it together. But these are take a lot of work before you can publish them, and often it's difficult to collect the right technical information if you're just letting people write whatever they want to do, whatever they want. What I would advise anyone doing this is to come up with some sort of something which looks a little bit like an observing proposal, and you can use like a Word document template. That's pretty easy just to set up. People might submit it with fields not filled out and things like that, so you don't have super good control over that. But it's pretty easy to set up, and for relatively modest numbers of people, that's okay.
Can you conclude, please?
Yeah, I think I've got 2 more slides left. I'll speed up a bit. What I would recommend is some sort of web form. Try and set up a Google form, and people can put in the narrative, add some pictures, and do put their technical information in, and that's good for lots of people. And then make sure you collect the technical and narrative parts at the same time. That's very important, a big lesson we've learned. Let's see. So this is my last slide now. So just to summarize what I've talked about, when you start a project, you must understand what the science goals are from the early days. And I've got here project promotion and technical information for the project. Those are sort of key areas that's important for. And then in order to do that, think about the process you want to follow that collects together all of the technical and scientific information, and all of this has to be done as you're building up the partnership, doing some design work, thinking about the costs and schedules of things. It's quite tricky, but you do need someone to run the process and you define it, and you have some workshops and meetings with astronomers, and get them to tell you what they want to do with the telescope, and start with that very early. And I think that's the last it. Yeah, that was the end of my presentations here.
Yes, okay. Thank you so much, Warren. And we will let the question for the end of the session. And Connie, you can.
Well, hello, everyone. And many thanks I want to say first to the organizers who have allowed me to present. I'm really thrilled to be here. I'm going to be presenting on the particularly optical observatory sites from the growing, can you hear me? Yeah, the growing satellite constellation interference. And with me on this venture are the wonderful team we have for the management team, as well as the co-directors or co-leads of all the 4 hubs I'll be telling you about that belong to the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or we affectionately call it CPS. Okay, so next slide, please. Oh, you're not even on there yet. Do you have me up there? It's the second one, Connie Walker, Protection of Optical Observatory Sites. Anyways, I can get going, I guess, while they're trying to get that up there. We're now on the second slide, sir. Okay. So you're going to see an image that's going to kind of astound you. Because it is of the Earth, but it's of thousands and thousands of satellites presently around the Earth. And what you're going to see in the second slide, thank you. Oh, do I? Okay, yeah, I'll try working with it. The first session, it didn't work so well. Okay, I have the controls. Thank you. That's good. So this particular image illustrates the challenges we're facing at the moment of a burgeoning new space era. And these dots represent the current number of active and inactive satellites, as well as rocket bodies and debris and some other uncategorized items that are up there. And as you can see, there's almost no place on Earth that you can actually be that you won't experience seeing them if they are bright in your neighborhood. And I'll talk about that in a few minutes. And also, there's not going to be any place on Earth that you won't experience them growing over the next few years. And that's what I'd like to talk to you about today, is both the challenges and the solutions of the increasingly large numbers and brightnesses of the satellites, and how they're going to impact our field, and how we as an international community should actually work together to protect our night sky and our field, and for all humanity as well, not just for our field, but for humanity in addition. Let's go to the third slide. Oops, are you not there again? Sorry, I'm trying to progress. Okay, well, this third slide is on the sustainability goals, actually. And let me see if I can advance it. I can't, because say it again, Zohar. No, I'm not. I don't have, well, I can't. They should be sharing the screen. Yeah, there you go. Thank you so much. Sorry about this, guys. This is, I want to direct your attention again to what Mirana said at the very beginning, the first talk, excellent talk. She was talking about the sustainability goals. And with all of the problems that the satellite constellations are presenting to our field, in reality, satellite connectivity has been very effective in providing internet connections to isolated communities. And I have to acknowledge that. That's a fact. And we're not trying to, in any way, IAU has no intention of hindering the operations of satellite constellations at all. But we have to acknowledge as well that this interference is having an impact, a negative impact on our field, and we have to try to work together to mitigate the situation. So let's go to the very next slide, please. Okay, so one challenge that we are facing is an exponential growth in the number of satellites, and over the last few years especially, and these are with mostly the commercial satellites, the LEOs, they call them, low Earth orbiting satellites. And right now we have about 10,000 active satellites that are up there. And then more than 500,000, closer to 1 million satellites that have been listed to be licensed to launch. And this is mostly with the International Telecommunications Union, and also in the United States, what they call the FCC. And that's a huge number that's going to be impacting our dark and quiet skies. Next slide. Okay. So this is a simulation. And a simulation is by Ollie Hano at ESO, and he did a simulation of 70,000 satellites, which were very fastly approaching. And in that situation, almost anywhere on Earth, you might have between 2,000 and 5,000 satellites overhead, right? So in the plot on the right, what you're actually seeing is the brightly lit ones that are coming about right now. Is at twilight. You'll see them in a moment, coming up at twilight and then getting brighter and then dimming again towards the middle of the night and then starting all over again. And I mean, they at twilight, both at night and in the daytime, you'll see more satellites, basically because the sun's hitting, reflecting off the satellites. So, and on the left-hand side, basically you're seeing from space, you're having a veil of satellites that are surrounding the Earth. And the blue dots on the top are the ones you actually see out of the tens of thousands that are orbiting, basically, in this simulation. So it's between, again, 2 and 5,000 you'll probably see. Okay, so what I'd like to do in the next few slides is try to capture what impact this is having on optical astronomy. And my colleague, Federico De Bruno, who is in the audience here, will be talking about the radio impacts to radio astronomy in another few minutes. Okay. So most of the observatories most of the observations done at twilight are to search for near-Earth asteroids, right? Near-Earth objects, and also solar system objects that exist between basically the orbits of the Earth and Venus. And these observations must be taken in the direction of the rising or setting sun so that they actually can have a, can be seen. And so the observations of potentially hazardous asteroids require very many detections in order in a very short discovery window in order for them to be able to determine their orbits. And so if the data that could help determine the orbit is lost due to some satellite trails that are crossing the image, then we lose the probability determination for collision with the Earth. So this is a very, very, this is actually, if we can go to the next slide again. I'm not paying attention to you guys up here, sorry. Can we go to the very next slide? Yeah, so there's the simulation on the right-hand side, 5 images being combined into one and then having a satellite trail basically obliterate some of the information. So, and then there's 3 other case studies I have here of different kinds of areas of astronomy that are affected as well. Okay, so how, I'd like to talk about a little bit, how are these observatories impacted. And after I go over a general case, I'd like to actually go into a little bit about what I found out as of late from 3 out of the 5 countries in Africa that are being represented here in this session. They have given me some information I'd like to share with you about the impact on their observatories. So in general, though, when a very sensitive optical telescope has an illuminated satellite in its field of view, the streaks that are produced are actually, they irretrievably cause the loss of data. As I was mentioning in the last slide, telescopes with larger fields of view are the more severely affected. So for the narrow field telescopes that view a very small part of the sky, the effect is limited and is predominantly at twilight. So maybe 10% of all their images might be affected. I'm giving a very sweeping guess here. But in general, they can avoid basically satellites if they choose to in that case, right? Or maybe just retake the data if they have to. In the case of wide field facilities, where they are looking at, a good sizable portion of the night sky, you're going to be more severely affected. Here, basically almost all the frames at twilight will be affected, and a few during the whole night. So like Vera Rubin Observatory, you're going to hear me talk a little bit about Vera Rubin. It's part of our family at NOIR where I work. And the Vera Rubin in particular will be affected primarily at twilight, almost every image, and then sometime during the night as well. Okay, so this next slide. Next slide, please. Okay, why don't we go to the following slide? Yeah. Okay. So this is a reality we're facing. On the left-hand side, you basically have simulation. Well, they're all simulations, actually, using the LSST camera on the Rubin telescope just as a case study. And they looked at 3 situations. One where it's just a streak that's below what a limiting magnitude of 7 basically is what's being asked for the different industries, to the satellite companies, to try to oppose to be less bright than 7th magnitude. And if you did that, you pretty much have the streak that you have on the left-hand side here, and you could subtract that from your images, more or less, right? You still lose the data underneath it, but at least you can try to subtract it. The middle panel that you see here is basically what the current Starlinks are providing us with a little bit more than the minimum value, which we're trying to still obtain. And so you have some residual streaks you could see on either side that kind of, present a problem. And it's not a very linear streak across, so you can't really subtract it too well. And then you have things like that are coming about more and more, are these communication, the satellites with the direct-to-cell huge panels of antenna, phased antennas on the like 8 by 8 meters at least, or 10 by 10 meter platform that is basically totally reflective. And this is what you get with Blue Orca 3. It attained, we had a paper out a little more than a year ago by the center, and it showed the highest magnitude was basically as bright as Vega. So about brighter than 99% of all the stars in the night sky. It was hugely bright. So that's a problem. Okay, so can we go to the next slide, please? So this past week or so, I've been in contact with 3 out of the 5 countries that are represented in this focus meeting. And from Paul Baki at the Technical University of Kenya, he was telling me that he thinks right now there's a very minimal effect of satellites on these various observatories that are listed here. And basically one of each of the countries I mentioned are listed here as well. So, but he did acknowledge that the landscape is changing and that we have to consider what the future holds, right? And that it could be a lot more than it is right now. But right now, for you all, it's pretty minimal. So let's go to the next slide, please. So in this next slide, we had Boskri, and forgive me, Zuhar, if I say his last name not correctly, but he works with Zuhar and the IAU-GA Observatory in Morocco, and he was very kind enough to give some, actually some GIFs, some simulations here that show latitude, or actually there's a number of observable satellites by latitude on the x-axis, and a function of time going around, as you'll see here. And it's over pretty much almost a week, I think, here he shows. And you can see mostly at the beginning and ends of the night, you see more satellites. Let's go to the next slide, please. Here's another simulation that he's showing, and this time it's the probability of detecting satellites, and he has a resolution of about 1 degree or so across the entire sky there. And again, if you can interpret that a little bit, it's also showing basically at twilight, at the beginning and ends of nights, you're going to be able to see more satellites. And this is from their observatory in Morocco. The next slide, please. Okay. And here he gives another, this time a histogram, and mostly it's of the brightnesses, the magnitudes that they are, they're projecting, and also they are confirming basically with what they observe. So, and so the number of satellites is on the y-axis here, and the magnitude, the brightness is on the x-axis here. And what we're trying to do is get better than 7th magnitude. So there are a fair amount of bright satellites there. And the number, if you can see on the x-axis, it does go above 1,000. And I think this is just for July 1st. They did this. Sorry, I'm a little parched here. Sorry. Now, from a totally different, next slide, sorry, totally different beast here. Something that I had never considered before is Gamma Ray Observatory. Next slide, please. Sorry, thank you. Okay, so this is actually the Gamma Ray Observatory that's Hess, and this is in Namibia, I think. And so Professor Michael Backus provided us with this information here. It's really interesting because, you know, if you do, they have a integration time of only 20 nanoseconds. And so if satellite comes by, it's basically going to be 1 pixel. It's going to be the same pixel no matter how many detectors you have around the area. Same pixels. You can take it out. But if over time you get tens of thousands of satellites up there, yeah, thank you, then you're going to have a problem. So let's get going here. Okay, I'm going to leave this next slide on radio astronomy to my colleague Federico, and he'll tell you all about that. I'm going to keep on going. Now, there's just a couple of things I want to say about the mitigations from our community and then the mitigations from the satellite operators. And first and foremost, we've been studying it a lot, and I'll talk about the center in just a minute. So you can have simulations and modeling that we've been doing already at our center, and other people around the world have been doing, like you saw from Buscree. And this allows observations to be scheduled, so if you know when they're going to, the satellites are going overhead, and you can actually try to avoid them if possible. Another measurement includes simply closing the telescope dome, but that actually, you have to know exactly when they're going to be going overhead. And if you do, though, you can close the dome, but a lot of people don't have that capacity, to be honest with you. And so there's other things you can do here too. You can redo the observations, like some observatories will choose to do, and you can do some post-processing, but not a huge amount. So, if the trails are optically faint, you can do it. I should quantify that a little bit, and you can try to subtract them from the images. So let's go to the next slide. But again, all of this is going to take time and money, right? But the next slide, please. I can try to do it here. There you go. Okay. All right. So this is mitigations by the satellite companies, and there are some basic mitigations that they've already done. Some like SpaceX has done, which I'll talk about in a second. That you could try convincing them that fewer satellites should be launched, but that's going to be kind of a futile thing to do. We have actually argued the point with SpaceX to lower their satellites in terms of altitude, which they have done actually. And we said this because they spend more time in the Earth's shadow and they wouldn't be actually seen visually, optically speaking. And they also are defocused if they're lower, believe it or not. You can use darker materials, which SpaceX has done, and they've used two different types. They paint the curved surfaces on the flat surface. They put sort of like a reflective mirror almost, and that reflects the light away from the Earth, basically. And they also use going over the terminator. They actually tilt their solar panels and the reflective parts of their satellite away from the Earth as well, so that it won't kind of get into the beam of the field of view of the telescopes, let's just say. So that's a couple of things that they have done, and sharing their data. That's another good thing, and attitude adjustments. So those are all these things that SpaceX we know has done, and they've also given their methodology to other companies to try to have other companies also take upon themselves to do these mitigation strategies. So let's go to the next slide, please. I'm going to go through this fast because I don't have too many minutes left, but the CPS is something you all should hopefully get involved in, if I can entice you guys. It is a burgeoning center. We've just started 2.5 years ago. We have an incredible crew of people, most of which do voluntary work, I have to say. We have areas in software and observations, which is called Sat Hub. We have a policy hub, which is obvious, both on international and national scales. We have a hub that works with industry and is amazing. Has done amazing work in getting in contact and getting industry committed. And also a wonderful group called the Community Engagement Group, which gives a voice to people who are outside our field, basically. So communities like the indigenous communities, planetaria, even amateur astronomers, all sorts of communities are involved. And so let me go on to the next slide, please. I have a representation here. It's sort of like a model, I call it a model of cooperation with these 4 hubs involved. And this is what we do to achieve, try to achieve success, basically. Let me go to the next slide, please. I'll just talk very briefly. Okay. So for the SAT hub here, it's the Software Observations and Analysis Hub. And let's go to the next slide. I'm trying to go fast now. I'm so sorry. These are the various areas they've already accomplished. Oh, there's sorry. Yeah, I gotcha. Thank you. If I can go, just spend, Yes. Okay, so they've done various things here, and mostly it is in a wonderful program. They're now trying to model the brightness and the positions of various satellites and putting them in use so that we can have a program that any observatory around the world can use to try to avoid satellites, for instance, or especially over a certain brightness, which affects individual observatories. They also have a data repository, and that's a really big deal as well. If you want to learn more, I can tell you about that later too. Let's go to the next slide, please. The huge thing that happened the last couple of weeks, we won a big grant from NSF, yay, to do exactly this, the software and observations kind of aspect of SatHub. So, and I can tell you more about that later too, if you'd like. So next slide, we want to talk about just the industry hub for just a moment. And they provide a safe zone for satellite companies to discuss mitigation techniques. And they have engaged both sides, I don't want to say sides, but both cultures, the astronomers and the industry, in adopting, trying to come together in terms of adopting the tools they could use for mitigations. And they have a new program called Astronomer Guides. And if you would like to be paired as an astronomer guide with a company, come see me. We can do that. And so, the next slide. So I've already talked about this. Let's go. We can't even see the bottom. But anyways, go to the next slide, please. Yeah. So we have the Community Engagement Hub, and I mentioned them a little bit already. They actually serve as the bridge, I said, to other communities that are not necessarily part of our professional field or the satellite industry. And they've done this. Let's go to the very next slide. They've done, the biggest thing they've done is this wonderful group of videos, 8 videos, very short, between 7 and 15 minutes, that talk to you about the challenges and the mitigation solutions. Next slide. I'm sorry if you can't hear me. Mitigation solutions that you could explain to industry, you could explain to the public, you could explain to other astronomers. It's very good. You can find that on our cps.iau.org website. And this, our last group is the policy group. Next slide. I'm sorry, I'm not very clear, I guess. We have, and this is an amazing group, so well organized, 10 different work packages. It's amazing. And they have everything from a sort of a policy paper they just finished that you can find on our desk downstairs if you'd like to see in the exhibit hall. And as well as a beautiful brochure you might find down there about CPS. And they make it a point to study space policy, to talk about national regulations and guidelines and frameworks. They've gone to the UN and all sorts of things that we've done to accomplish the goal of getting sort of policy out there in terms of satellite constellations. But let me show you the next slide. And this is some of their accomplishments you can see. Next slide. There you go. Beautiful. Thank you. And I'd say one of the coolest things has been giving advice in terms of what we could do in terms of the UN Committee for the Peaceful Use of Outer Space. And I'm going to actually go to the very next slide, please. Do you want me to do it? Oh, there you go. Okay. Yeah. This has been the huge accomplishment I want to brag about because it took about 4 or 5 years to establish the fact that astronomy is a space activity at the UN. And this is the Committee for the Peaceful Use of Outer Space. And they have another group under that called the Science and Technology Subcommittee. And it's in that group now that we have a 5-year agenda item that's dedicated to dark and quiet skies in relationship to satellite constellations. This is a huge accomplishment. And I know that Federico is going to be talking more about the group of friends, which is behind all this and helping make this happen. So he'll tell you more about that. So just to mention, if you want any more information, let's go to the next slide. This is a place you have to go. Take a picture because you can find out about what our community is doing at large and what the CPS has been doing. We just had an incredible symposium last fall, an IAU symposium. And then the next slide, please. If you want to join us this week, please, 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 we have little handouts here for you that James will help pass out now if you'd like. And we have handouts on both our working group meetings. One is actually the CPS. The center is tomorrow, all day. And then on the 15th, we have one on ground-based light pollution. And the last slide, I think. Oops. Oh, please, if you want to pass it out, yeah. Oh, sorry. We're going to have meetings in the future. Oh, the previous slide, sorry. We have meetings in the future, one in 2025, probably in Manchester, and maybe Federico could tell you more about that too, because that's his hometown. And then in 2026, possibly we'll have a Dark and Quiet Skies meeting in Chile. So please stay tuned. We're going to stay active. We are active. We want your involvement. It is very important. Okay, so please come see us and talk with us, and we look forward to talking with you. Thank you.
For this really nice talk. And, we now have another invited speaker, Ramatolo from South Africa, and he will speak about dark sky protection in South Africa. Go ahead. Okay, I would also want to thank the organizers for giving me an opportunity to talk about dark sky protection at South African Astronomical Observatory. Okay. Next slide. Next. Yeah, so I'll just briefly give you an introduction about the SAO and its history. Next. And I'll talk about the legislation that we use to protect the astronomy facilities in South Africa, as well as related regulations. And I'll go into current status of what's going on at the observatory now. Next. And I'll talk about challenges that we have. We're trying to do all of this. Next. And next. So I think basically the South African Astronomical Observatory is one of the oldest observatories on the African continent, as you already had this morning. So our headquarters are here in Cape Town, and the telescopes that we have are in Sutherland. And the telescopes you see here were the first ones. Next. Were the first ones that, next. The first one that were, oh, okay. Hello. Okay, well, the first telescopes that went to Sutherland in 1972, when the observatory was formed from what was called Royal Observatory in Cape Town, where you see these buildings now, where they still house astronomers that work at SAO, and the telescopes moved from Cape Town and Johannesburg to Sutherland. Next. And so this is Sutherland currently, and you have already heard about all of these telescopes, but I will be mostly talking about this little thing here called ASPONS. This is the all-sky monitor that actually we use to monitor light pollution at sky brightness. And it's used in conjunction with the regulations that we have basically to protect the night sky at the observatory. Next. Next. Okay. Next. Okay, in fact, before I go into this ones, as far as the telescopes are concerned, I think it's important to tell you that the telescopes we have, let's say the 1.9 and 1 meter telescopes that we talked about earlier this morning, they are basically available for anyone around the world. Whoever would like to apply for time, you are free to do that, and your project will be looked at, and if it's scientifically
good enough to be offered time. It can be offered time. We can be able to do observations now remotely. And on one of the telescopes, you can even do it robotically. So the main legislations that we are using is called the Geographic Advantage Act of 2007. So this is the main legislation that we use to protect astronomy and related scientific endeavors in South Africa. Next. And out of that, there are related regulations. One is called the Regulation on the Protection of the Southern Central Astronomy Advantage Area. Next. And the other one is the Declaration to Prohibit Certain Mining Activities within Southern Central Astronomy Advantage Area. And this were sort of enacted in 2019 under notice 805 and 06. And okay, next. Next. So basically the act itself is basically empowers the Minister of Science and Innovation to declare protected areas around strategic astronomy sites, or what we call astronomy advantage areas. Next. And it covers both radio and optical astronomy. Next. And it also makes declaration for the establishment of what is called Astronomy Management Authority, which has already been done. So we have Astronomy Management Authority within the Department of Science and Innovation, and that entity is the one that we are working with at SAO to try and make sure that the regulations we have are not actually infringed. Next. So the protection of these regulations has got 3 tiers, the core, the central, and the coordinated. So I'll be mostly talking about the central area because that's where there are issues, because the land around that is not necessarily owned by SAO, whereas the core is owned by SAO. The central, in this case, is it's about 75-kilometer radius from the Southern African Large Telescope in the Northern Cape. Next. So this is the Central Astronomy Advantage Area. So here is in the Northern Cape. Here, the gray, the shaded area is in the Western Cape. So the protected areas are around here. Next. 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 So the regulations actually covers things like prescribed conditions for lighting activities within the Southern Central Astronomy Advantage Area. Next. And activities creating air pollution, and regulations on wind turbines within the Southern Central Astronomy Advantage Area. This only covers the large wind turbines. So basically, and even within 20 kilometers radius of the observatory, we don't allow any wind farms at all. Next. And it has some annexures A, which certainly we just gives sort of the details of the moonless night sky brightness that should not be exceeded. Next. And another annex, which I'm not going to go into, so more about the dust levels and stuff like that. Okay, next. So this appears in Annex A. So these are what we call the natural levels of the night sky brightness at Sutherland, and the extinction values. And these numbers are not supposed to be exceeded by any outdoor lighting around Sutherland. Next. Next. So I mentioned the declaration to prohibit certain mining activities. So activities that are prohibited under this declaration include So for mining, next, and hydraulic fracturing. Next. Okay, currently there are things that are going on that we are dealing with in Sutherland, like there's this construction of massive number of wind farms around Sutherland, but most of this we had sort of consultations with them as well with South African Civil Aviation, which basically requires them to have lights, but sort of have some mitigation measures. Next. Yeah, there are other issues like prospecting applications that Astronomy Management Authority and SAO are actually dealing with, which really is just a nightmare at the moment. And some outdoor lighting issues in the Sutherland town, which is just 15 kilometers away from us. Next. But I think the good news is that the moonless night sky brightness levels at SAO are still close to what the natural dark sky brightness levels quoted in the regulations look like. Next. Okay, this is sort of a light curve taken with the little instruments that I showed you earlier. So they take like within every 5 minutes, they go through BVRI filters, taking measurements of the night sky brightness every night between twilights. So this is the light curve, but the whole light curve basically, including the moon times basically in 2024. Next. And this is the same light curve with we're removing the data that's affected by the moon. Next. And so actually that's zenith, so pointing straight up. And this is the same similar light curves in B, V, R, and I. So these are magnitude per arcsecond squared for this year. And you can actually see that there's not much difference, but okay. So these are, you can actually see the averages. And this ones actually include actually so basically the data that's not clear skies has been subtracted as well. So these are clear nights. Next. Same thing for pointing at different directions. So this is north, that's east, south, and west. And I think looking at this, you can actually see that, whatever you see here that may actually look like some issues, it does not necessarily appear to be coming from the ground, because if it was, I would expect that it will be only one direction that's affected. Next. So what I showed you now, so this is the results of so the average brightness per year at the observatory since 2016, and you can see that the numbers do not actually change that much. So we don't necessarily think that there are serious issues as far as light pollution is concerned at the observatory at the moment. Next. So this is the same for pointing at different directions, and you can see that the numbers in V are exactly the same for both the mean and the median. So yeah, looks good. Next, and exactly the same as what we quoted in the regulations over time. So, next. Okay, the challenges that we have is, I mentioned that we have had consultation when the wind farms were coming up in Sutherland. The South African Civil Aviation Authority had agreed that they will have parallel regulations governing the lighting on and off on the wind farms. but it looks like now they are sort of they're no longer interested in doing that. I mean, there has been lots of changes within the Civil Aviation Authority institution. So this is a serious issue because, okay, thanks. A lot of the agreement with the wind farms was based on the premises that the lighting on those wind farms will only happen when there are aircraft passing above or within the vicinity of those wind farms. So if we don't necessarily win this case with the Civil Aviation Authority, then we may have issues. Next. And then, and also there are some issues with, so basically Astronomy Management Authority is within the Department of Science and Innovation. So basically we do work well with this entity, but one of the issues is that they work with the legal team from the Department of Science and Innovation, and sometimes there's sort of different interpretations of the regulations, and so it looks like sometimes it will be very, very difficult for the legal team to actually work with us or agree with us if there are some issues that they may end up actually them having to represent us, or maybe even in court. Next. 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 Yeah, okay. Yeah, I think one of the other issues with a really serious challenge is that the protection regulations that I mentioned and the declaration to prohibit certain mining activities in the Southern Central Astronomy Advantage area, they do not mention prospecting. They only mention mining. And there are companies that are taking advantage of that, and they would say that they're doing prospecting instead of mining, and then they apply to go into those areas that where mining is prohibited. Next. And this is an example of one of those, the observatory is there, and this company has got licensing to do prospecting there, which is right in our neighborhood. But this is done by the Department of Mineral Resources in South Africa. So there's sort of some issues between this government department and Department of Science and Innovation where astronomy management sits. So that's another challenge. Next. Next. Okay, I think that's close to where I would end. And I think the lessons that should be learned here is that we probably need education of the communities and stakeholders around the observatories regarding light pollution mitigations and benefits of keeping our night skies dark for science and humanity, and better communication in our case between government departments should really be prioritized to make sure that there's not really, they're not impacting each other negatively. And one of the things that I used to think that is really necessary for this kind of regulations and protection of the night sky is actually voluntary compliance with whatever regulations we have, but it looks more and more difficult with some of institutions. So I'm actually glad that we have these regulations and prohibitions, even though there are challenges. But I think that it's still better than to rely solely on voluntary compliance. Thank you.
I will quickly go to Federico Di Verno. It's from SKA Observatory 2. Okay.
Perfect. Thank you. All right, great. First of all, can I confirm this thing works or not? This. No, perfect. So I don't have it. I'll just say next slide. All right, good. So while the slides are coming, first of all, thank you very much for staying until the end. That's great. And to explain that you're wondering maybe right now what the radio guy is doing up there. You maybe think of radio astronomy as light waves in a very, 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 very low frequency. And we fit, right, in this discussion. So, all right, I'm Federico Di Bruno from the SKA Observatory. We are a radio observatory. And hopefully I can tell you a little bit about what we do and what's the situation with large constellations and radio astronomy. Connie was talking a little bit about that. So let's go. Next slide, please. Just a little bit about the SKA one back. Thanks. SKA Observatory. We are an international intergovernmental organization. We have 3 sites and 1 observatory. We have our headquarters in the UK, and we are building 2 of the largest radio telescopes in the world in South Africa and Australia. We have 10 member states, as you can see the flag there with the asterisks, 6 observer states, and 8 African partner states, where we hope that someday the SKA can expand into the African continent. Next slide, please. These are some pictures of the SKA MID in South Africa. In South Africa, we are expecting to have 197 fully steerable 15-meter dishes, including the existing 64 Mercat dishes. Our frequency range will cover from 350 megahertz up to 15.4 gigahertz, and we will have a maximum baseline of 150 kilometers. Next slide. In Australia, we will have the SKA low, or low frequency one, where we will have in the order of 131,000 antennas grouped in stations of 512. And it's a very impressive thing. So you have on the right, that's an artist's impression of the SKA low. And surprisingly, it's starting to look like that. So you'll see some pictures next. The frequency range of SKA low, of course, is very low frequency, 50 megahertz up to 350 megahertz. And we have a maximum baseline of 74 kilometers. Next slide, please. Yeah, and then some pictures of actual construction, right? The first thing was an image. Now these are real pictures of the site. This is one of the clusters in SKA low, and you can see 4 of those clusters which have a different bright gleam to them, and those are the ones that are populated with antennas. As you see here, these are 256 antennas individually sampled, so the amount of data that this thing produces is insane. Next please. Text. So this is some pictures of the construction in MID. So this is the South African site. This is what we call the big lift, where we lift the reflector of one of the 15-meter antennas. And you see that down there in the picture, the Mercat telescope and the big lift there on the left. It has, of course, its very big challenges to build the telescope in the same site where the telescope is operating. We can talk about that if anyone is interested. I'm not going to go into the details, but we can discuss that about the interference that our construction produces and so on. Next slide, please. And last thing about the SKO is that we have our 2 sites in very protected remote areas. So both our sites are protected by radio quiet zones. And what a radio quiet zone basically means, it doesn't really mean that nothing can emit in there. Right? That's a little bit of a misconception that comes from the name. A radio quiet zone is a geographical area where the use of the radio spectrum is specially managed, right? So we have special protections, as Ramatolo was talking about before. There are lots of protections that have a lot of processes to enable or to license transmitters in them. So this is a very protected areas, and as you can see, are huge areas, right? So these areas also include towns in there. So it's a challenging process to try to keep the sites as quiet as possible in the radio regime. Next slide, please. Okay, so that's all I'm going to say about the SKO specifically, but if you're interested, please have a look on Friday 9th. We will have a full day of SKO. you can see the information on this particular event is on the scientific events. I think it's in the program website of the IAU-GA. Next slide, please. And the interesting thing is that all our speakers are women. So if you want to know more about the SKA, you can find out from our wonderful female colleagues in the day of the Women's Day on 9th. Next slide, please. Right, so Connie made a great introduction to this, so I don't have to delve a lot on this slide, but basically we have facing new threats from the sky, right? The sky is from space. Space is getting crowded and crowded. And what's happening is that the likelihood of having a satellite in front of our beam is increasing, right? We cannot say that this is a new thing, right? Radio astronomy has been dealing with satellites for forever, but the situation is changing a lot, right? And these satellites are producing radio and light pollution, as Connie was saying before, and radio quiet zones do not formally apply to satellites, right? Radio quiet zones are very effective on the ground, right? But when things are in space and we see them in the sky, it's much more difficult to control them through the radio quiet zone regulations. Next slide, please. Connie explained this very well, so I won't go in detail. Also, I don't know as much as she does. So let's go to the next slide, please. And yeah, a little bit about the radio impact. So if you think that the radio telescope is just one antenna or a collection of many, many big antennas trying to listen to these very faint electromagnetic signals coming from stars or galaxies or whatever. And you have some satellites going around, next slide, that can produce very strong intentional emissions, so downlinks, right? The satellites, of course, need to connect to the Earth. They want to provide internet connectivity on something. So we got very, very strong signals coming into the ground. Next slide. And we also have other effects, such as unintentional electromagnetic emission, right, or UEMR. And this thing is not so strong in communication terms, right? So if you compare the unintentional emissions of a satellite with the intentional emissions, these are way, way, way weaker than the other ones. But in astronomical terms, they are still very, very strong. Next slide, please. So a little bit on the two of them. So the intentional downlinks, these are very strong signals, and they can saturate receivers. They can interfere with allocated radio astronomy bands, so the bands that are reserved, the pieces of the spectrum that are reserved for radio astronomy. So emissions in there can interfere with these bands. They can block big parts of the radio spectrum, right? There's a thing that we need to realize, that the radio spectrum is divided in bands, and each band is assigned to different users. So sometimes it can happen that a big portion of the spectrum is just used by satellites, and we cannot access it. So the frequencies normally for intentional downlinks are about 2 gigahertz, 1-ish now, depending on what thing we're thinking about. And the unintentional emissions, the thing they have is that they are normally not constrained in frequency, right? If you think on intentional downlinks, you can find exactly the frequencies that some satellites are transmitting, but that doesn't happen for unintentional emissions because they're unintentional, right? So they can be generated in any frequency in principle. And they are quite intense if you think on astronomy terms, so in the order of 1 to hundreds of Janskys. They are not regulated normally, so there's no regulation, whereas for intentional downlinks, there is a regulation. For unintentional emissions, there's no regulation in place. And it normally happens in lower frequencies, so under 1 gigahertz. Next slide, please. All right, so what are we doing about this? Connie mentioned a little bit of this. So some countries are trying to put some conditions in the licensings of these constellations. So when a constellation wants to offer the service in the country, some countries are starting to put some conditions to protect astronomy. Not all of them, I would say the least of them, but that's starting to happen. We are working at the ITU, the International Telecommunication Union. I'll talk about that later. And we are working in the UN COPOST, as Connie also mentioned. And we are, of course, working a lot in the IAU-CPS. Luckily, Connie mentioned everything, so I'm not going to go into that. And we at the SKO and several other observatories, we're working on software mitigation measures, right? We need to put software in place to try to deal with this. Next slide. Thanks. So on the ITUR, the ITU is the International Telecommunication Union. It's a UN agency that regulates the radio spectrum, right? So they define, all the countries really define how to use all the different frequencies in the radio spectrum. And in there, we are a sector member of the ITU, so we go there and we advocate trying to protect astronomy. And we have a very, very good cooperation with Sarao, with the AMA that Ramatolo was talking about, and with ICASA, who is the national regulator in South Africa. We collaborate very well with them, so we have obtained, let's say, I don't know if it's the best word, but we got an agenda item for the World Radio Communication Conference. This is the conference that every 4 years revises the international treaty that defines the use of the radio spectrum. And so that's where I was talking about that some emissions have a very well-established regulatory framework. Right? So every 4 years, there's a revision. And right now for 2027, we are working, this was established in 2023, right? So in 2023, we got this agenda item, and now we need to work until 2027 to argue that we can protect radio quiet zones from satellite constellations. And this was mainly possible thanks to the African continent. Right? I think that's a very, very important thing to remark. We got a lot of support by the African Telecommunication Union and spearheaded by South Africa. So the support from them was instrumental to get this agenda item in place. Having the agenda item in place doesn't mean that we will eventually get some positive result, but it already means a lot, right? So we need to keep working on that. And we are also working on a report on UEMR and intentional emissions. We are working on that at the Working Party 7D in the ITU. And that's also a very important work because, as I was saying, unintentional emissions are not regulated. So if you go into the ITU and you argue that these emissions, this radio noise from satellites is producing interference, the ITU will say, well, okay. So this is what we are working on right now in Working Party 7D, trying to raise awareness and eventually leading into regulations. But we need more support on this one. Next slide. Okay, that's good. Connie did mention a little bit of this, so good that you all know what the UN COPWAS is. And she also mentioned what there's an agenda item that will last for 5 years in the Scientific and Technical Subcommittee of COPWAS. This is a very, very important thing, and this is my personal opinion in here. So it's not so much for what the regulations will come from COPWAS, because there won't be any international regulation from COPWAS. It's likely that at some point there might be guidelines that come from COPWAS, international guidelines on how to protect dark and quiet skies. But what is very important from this work is that anyone in a country can go to the regulator in the country and argue that there is a lot of discussion in this very high-level committee at the UN, so you can get a lot of traction at the national level, right? I think this is one of the most powerful things about having an agenda item in COPWAS. And Connie did mention that there's a group of friends for dark and quiet skies. So this is an informal group within COPWAS. And the interesting thing about this informal group is that experts from the different countries can participate in this group, right? So you, as astronomy experts, can get in touch with your regulators or the mission that goes to COPWAS, and you can contact them and tell them and say to them, like, I'm interested in working in this group of friends, and we are working right now in creating some focus groups that will work on particular technical questions, and that is something that you guys have something to add to it, right? So you can definitely work on this. Happy to talk about more on this offline if you wish. Next slide, please. So I think this is the last one, and about the opportunities for Africa, what Africa can do. I think one of the most important ones is these questions about licenses for satellite constellations in the countries. While the idea of having international regulation is nice, and it would be very good if there were, The reality is that the power we are seeing from conditions or trying to get the operators to talk to astronomical observatories is these conditions for the licenses to operate in the country, right? So if there are these different operators that want to operate in the country, if you get your regulator to say, well, the condition is that you need to coordinate with my observatory in the country, this is what the US is doing, for example, it's very strong, right? Because if they don't talk to the observatory, they don't get the license. This is very important. Yeah, I'm almost done. And the leadership on the agenda item 1.16, in particularly for radio quiet zones, this is very important. And then we hope that the African continent and the South African regulator are still going to support us. As I said, this was instrumental in WRC 23 to get it. And as I was saying before, right, the participation in this group of friends, it's only up to you, right? It's quite informal to participate in this group. So the only thing you need to do is find out who are the people that go to COPWOS, and you can just contact them and say, I'm interested in participating in this, in helping you. This is what they really need. These are diplomats, so diplomats don't know much about the specific topic. So you can give support for the diplomats that work at COPWOS in the technical focus groups that we're creating there. And I think that would be it. Next slide, please. Yeah, thank you very much for your attention.
Federico, we are late. The opening ceremony will start soon. If you can have 2 or 3 questions about the anti-function. Is there any question? Otherwise, we have at the last session tomorrow, the discussion slot, and we can exchange about this topics. Yes.
Hi, thank you. James Lowenthal from the United States. I have a question for
Ramotolo, can you say a few words about what you think has been the most effective kind of messaging when you are trying to convince your national agencies to talk to each other? Is it mostly about money, you know, the economic benefits of mining versus the economic benefits of astronomy, or is there some other value that is at play in the discussion?
Thank you. I mean, it's not really clear to me. As far as things like wind farms, for example, I mean, we definitely have issues with energy in the country. So we do see the need to have them within those areas, but actually just have mitigation measures to address things like light pollution from those kind of things. That's why we had all the, you know, sort of the consultation with the Civil Aviation Authority to, you know, so come up with options that can have the wind farms and us coexisting in those areas. As far as mining is concerned, like I said, that we actually have prohibited mining within that 75-kilometer radius. I mean, the difficult thing is that the Department of Mineral Resources, it's basically, you know, for them to license mining, you know, it's their KPIs. So basically, that's what they do. You know, every year they say, well, this is the number of licenses we have dished out. So, which is, but I mean, the South Africa is quite a large country, and even the Northern Cape, which where the astronomy advantage areas are, is the largest province land-wise in South Africa. So 75-kilometer radius is really a little, it's nothing. So they can actually do something else outside that area, which even though we may not necessarily like it when they're closer to us, but You know, I don't think that's you know, we can do anything if they do something else outside the area that's protected. Thanks.
Can I ask?
Yes,
Okay.
yes, please.
Thank you, Professor. So, actually, I have a question regarding the results you actually showed. I've seen that you say that should do about 25 magnitude using your tool. Is it reasonable to 25 magnitude?
Yes.
Hmm? And I've seen that in all bands.
Yes, yes, in the
Okay.
No. It was B-band.
which instrument you use for this value?
It was BVRI.
Yes.
Yeah. So which one you have issues with?
I think
The limit is
Yeah.
22.
K, if the magnitudes are above, you know, the
Yes.
so I don't know what that means.
Yes, I mean, yes.
Yeah.
I think the instrument need to be calibrated.
Limit I use, that's what's coming out of the instrument. You know, but anyway, I just don't think it's I think the main issue is if the brightness goes which would mean that there's some issues with light pollution. But I don't necessarily think that the instrument is actually calibrated, you know, to a certain maximum number. But there are other issues. That's why a lot of things that I subtracted lots of things like, you know, data that's
Is there any other question? Warren is still with us. If yes, David. Yes.
May I ask Warren a question, please? Warren, you started saying that we can make science goals or science book just after having the idea of constructing a new telescope. Does it depend? I mean the probabilities of the characteristic of the site itself. The characteristic of the site itself can affect the science goals or science book from the beginning.
Can you hear me?
Yeah.
Yeah, they can. All of these things are interrelated. So having everyone wants, lots of clear nights, and good turbulence characteristics and things like that. So you can pick any kind of decent site at first, or that can be your baseline, and perhaps you as you get a better understanding requirements for the, so you may change the idea for the site that you want. You probably have a few sites at first, and you identify 2 or 3 of your favorite sites out of that group. So I think the answer to your question is it's everything is somewhat related.